Hello everyone, welcome back to my channel Deep Understanding of Research Papers. Today in this tutorial I will explain a recent paper called H vectors, utterance level speaker embeddings using hierarchical attention model by these authors, and this paper is coming from Sheffield University in London, and the tutorial is going to cover the introduction, then model architecture, then some experiments and result, and finally we'll see some visualization. So what is this H vector? So basically people who are working in speech domain, or the researchers or some speaker identification, the people who have worked on speaker identification, speaker verification, will know about this model called X vector. So this X vector basically was proposed by Daniel Povey and his team, I think back in 2018 or 17, to do something called speaker verification, or short term SV or SI. So speaker identification and speaker verification, they're almost same. So just assume some sort of identifying speaker is the speaker verification or speaker identification. And this paper got a lot of traction from speech community, where these people were generating very good speaker discriminative features, and that time it was state of the art paper, and I think the same idea was used for language identification, and it got best paper award in Speaker ODC 2018, I guess. So this idea of this X vector is to create a robust model or a neural network which can give you a utterance level feature vector, which can be of any dimension. Let's assume 512 dimension vector for every speaker, not for every speaker, for every speech utterance. You get one vector, and if you visualize these vectors in 2D, similar speaker voice or sentences will cluster together very well. And that is the reason this paper had other few techniques also, like doing something called statistical pooling and so on, but this paper was a very nice paper, and in fact I have tutorials of these papers on in my YouTube channel. You can go and check them out. And so the idea was to build a model which can give you highly discriminative features irrespective of utterance length, right? So that's why it's called utterance level speaker embeddings. And the paper basically, the X vector paper was actually built using something called time delay neural nets, and we'll see what the architecture they use in this paper. And that was X vector. And what is this H vector they are mentioning here? So this H vector is basically they are using because of this hierarchical attention. So what they are trying to do is they are trying to do the same thing. They are trying to create utterance level feature vector, which is robust to the speaker discriminative which are very helpful for speaker discrimination, basically to get the speaker identification works very well. And that is the idea of this paper, and they use the attention mechanism, which I think many people who are doing deep learning will know about it. So the idea of attention is to look at different parts of the speech signal and use those relevant speech signals or information from those features to do the prediction, so which is very helpful. And if you see, the speech content will have local and global information. So basically the local information, I don't know about, they have not showed okay what is that local information they extract, but basically the local and global informations will be speaker identity basically, and local information we refer to this phonemes and so on. But here they are saying they want to extract this local and global information using local frame extractor, the frame extractor and segment level feature extractor. So the frame level encoder basically is will work on the direct the spectrogram or MFCC features, and it extract features from those signals, the direct audio signal. And these frame level features are basically uh, uh, pooled, and those are fed into a segment level encoder. Basically we'll show you the diagrams and so on. So the segment level encoder will encode these frame level features into segment level feature, and that can be used for a used as an utterance level representation, right? And they are doing experimentation with the switchboard cellular corpus and call home dataset, and the testing was done on I think the testing was done on the training was done on the SRE data, and testing was done on switchboard, cellular, and call home dataset, right? And in this section, we'll understand this model architecture completely, like how the network is, the neural network, and we'll see these frame level encoders and frame segment level encoders. So this is the full architecture. Think of it as the flow goes like this from top to bottom. So you have a raw audio, basically the audio waveform, maybe 3 seconds, for example, assume, and you get these MFCC features, right? For every 10 millisecond you can extract, sorry, every 20 millisecond 25 millisecond window with 10 millisecond shift you can extract these frame level features. So this is just frames, right? Acoustic frames. Now what you could do is you can group these acoustic frames or MFCC features into for example chunks of 30, right, which corresponds to maybe 300 millisecond segment, right, 30 frames, and you group them into non-overlapping segments, and you use a network which is shown here. This is the same network which is replicated. I'm just, don't get confused that these are different networks. It's the same network, but since they are doing time axis, they're just replicating this. Just assume every segment will go through a network which consists of convolution layer, gated recurrent unit, basically captures the temporal information, which is like LSTM. Then you have an attention, so the output of attention will be pooled, or you can obtain the you can just get a single vector which represents the entire sequence of vectors. So that is done with statistic pooling, which combines mean and sigma. Just we'll explain that in later. Then what happens, for every segment you get sequence of for every segment you get one vector, and if you have 3-second window, or if you have a 3-second audio, I get 10 of these chunks and I get 10 vectors here, right? Simple. And these 10 vectors will again go through CNN and attention. Then they again do the statistic pooling, and that will be finally fed into a fully connected layer to do speaker identification, and you can tap one of the like last layers output and use that as the embedding. And here there are two things. One is frame level encoder. As you can see here, we encode these 30 frames using this and generate a vector. That's why it's called frame level encoder. And these frames outputs, there's for every 300 millisecond whatever frames we get, the whatever features we get, we put them all as a sequence, and then we encode that using segment level encoder, which is simple combination of CNN and then attention along with statistic pooling. And finally we'll do the speaker entities, or you can just extract the embedding and use it for speaker verification. As simple as that, right? So I hope you got the gist of it. It's very simple. You take the audio, raw audio, it can be 3 second, 1 second, 2 second, whatever, and you segment them into if it is 3 second, you segment them into 300 millisecond chunks. If it is 1 second, you segment them into 100 millisecond. Basically they are saying whatever the sentence length is, we'll cut the sentence into pieces of tenths, right? So that is the idea. So that's why I said 30. Then you feed them through sequence of CNN and GRU along with attention. Then you pull them and you do the same thing for all segments, and those segments you again pull them to get a Utterance level vector. So simple as that. Now let's go and understand in detail like what is there in the frame level encoder and attention. I think it's not a, I mean, I don't have to explain this in complete detail because many people will be knowing about what is CNN, what is GRU, what is attention. I'm just putting the equations in front of you. So what's happening is, as I said, we divide the utterance into sequence of pieces of 10 in segment. Assume this is 10, and you have 3-second audio data, and you get sequence of chunks which are basically for example, I'm representing one segment SI, which is the ith segment by the sequence of features. So if I have 300 millisecond, I get 30 frames, right? So this M is 30. So the L is basically maybe 13 if you assume, because your MFCC dimensions could be 13, and that is represented like this here. Then what happens, you feed this xi, which is a 1D vector, into 1D CNN. So 1D CNN output will be this prime, and then you feed all of those things into GRU, which is basically bidirectional GRU. So you have left and right hidden representations, then you combine them into single vector. So basically one equation missing is hi comma t is nothing but concatenation of h arrow forward comma t and h backward I comma t, right? So basically this is forward and backward hidden representations are concatenated and you get a single vector, and that you feed it through something called attention layer. So attention layer is very simple. So what happens is you have to compute this alpha I comma t, basically attention weights, and you can do that by simple MLP based attention or dot product based attention. Here they are using MLP based attention. So simple thing is you just take the inputs which are basically h and you just feed it through MLP, and then you apply the softmax, and those alphas which are basically the attentions will be multiplied by the hidden state representations, and then that will be fed to something called statistic pooling layer. So the statistic pooling layer, what it does, it if you have sequence of frames like this, so what it does, it computes mean vector and standard deviation vector, and then combines or concatenates both of them, and you get this the segment level, sorry, frame level uh, feature vector, which I showed here. I think this sorry about that, this one vector, right? So then that is about attention frame level encoder. And if you look at segment level encoder, it's the same thing. So what happens is you have all the so the I think one thing missing here is I think I have skipped something here, but don't worry about that. So what happens is if you go back and see here, here you have a CNN, which these are the segment level sorry, segment vectors, and you feed them to CNN and attention, and then you do statistic pooling. That's exactly what's happening here. You have z's and you compute alphas, which are the attention weights, then you compute mean and you compute sigma, and then compute the final utterance level feature vector, frame vector, and then following by you do the fully connected layer, and you do softmax, right? As simple as that. So I hope you understood it. I mean, it's not that complicated or anything. It's very simple. In fact, recently I submitted one paper to ICASP, which almost does the same thing, but that was written for gender identification, and I use something called multi-scale CNNs, which basically a sequence of or parallel CNNs which will process raw audio, and then they predict what is the gender. It's a kind of similar thing, but those were also getting utterance level vectors for these genders. So that is a different story. I think the deadline for ICASP is, I mean the paper acceptance for ICASP is in 24th of this month, which is just 4 5 days. We will know the results whether this paper my paper will be accepted or not. I have submitted 2 papers, so if they got if they gets accepted, then I will do the tutorial of them. Then you can see the paper, and I also put that paper in archive or somewhere, right? And sorry about this experiments. They are using NIST SRE for the training and call home data, and switchboard cellular part 1 data for testing, basically the evaluation. So the data set statistics are like this. You have SRE 8, which is basically has 1336 speakers for 640 hours of audio data and so many utterances, 31 second utterances and 3 second, and the same thing which CHE and switchboard, but they have less number of speaker and amount of data is also less. Coming to the experiments, like details of what is the input and all. So as I said, we split the utterance into sequence of equal 10 chunks. If it is 3 seconds, you get 30 frames. If it is 1 second, you get 10 frames, right? And then this is standard. You compute frames. I mean the MFCCs for this configuration. Then you have I mean the dimension of the MFCC feature is 20. Then as I said, evaluation we use call home and switchboard. Then for backend we do dimensional reduction using PLDA and reduce the dimension to 300. And this is the structure, or this is the configuration of the model. For frame level extractor, you have CNN, bidirectional GRU, attention, all these things, and then segment level you get this. So this is just simple statistics of or inputs output configuration of the model, and you can get all these things in Keras. If you just print your model, it gives you this kind of diagram. And coming to the results, for SRE, 1 second and 3 second you can compute the accuracy. You can't compute EER because you don't have the evaluation data. You can just compute the accuracy on the test data. If you use X vector, you get 90. If you use X vector plus attention, you get 92, and if you use H vector, you get 94, which is very, very good. You get 3% improvement in performance compared to the X vector model, and the same thing goes with the 3 second test data also. And if you look at equal error rate, you can compute equal error rate for call home and switchboard. You know the previous models, ER also. So for 1 second, the X vector is getting around 1.94 ER and so much accuracy. H vector is like the state of the art as of now. So I'm not sure if there are any other paper which claim they are better than H vector, but I'm assuming this is the latest paper and this is like the state of the art model, and it is state of the art for both the 3 second and 1 second. And same thing goes with the call switchboard data set also. It's very nice. So this is like the state of the art paper. I'm not sure if they have submitted this paper to ICASP. If they had submitted, I think they can. I think that this paper will be accepted. Not sure, but we'll know the results, right? Coming to the visualization, as you can see, X vector plus attention, and H vector. So as you can see, H vector is like has the best clustering and less mixture or mixing of one of the embedding into the other classes, right? This is like very good. These are speakers basically. So speaker 1, speaker 2, and so on. Some different speaker, right? And thank you so much for watching this tutorial. If you are not subscribed to my channel, please subscribe. And if you like this video, give a thumbs up and subscribe to my channel. Thank you.